Hello and welcome back to our journey through the solar system. So today we're making it into the outer portion of the solar system and we're going to talk about Jupiter, the king of the planets, named for the king of the gods. Actually by coincidence, because back when they named it, they did not actually know that Jupiter was the biggest, most massive honking planet in the system. So Jupiter was the Roman god of sky and thunder and the king of the gods of the Roman pantheon. The similar counterpart in Greek mythology was, of course, Zeus. Jupiter is our most massive planet. It's over 300 times as massive as the Earth, and it's only about 1,000 times less massive than the Sun. So it's pretty big. And the radius of Jupiter is over 10 times that of Earth. This means that Jupiter's bulk density, that is the average density of Jupiter, is about 1,300 kilograms per meter cubed, which is actually denser than water, but we call Jupiter a gas giant, so how is this gas? Well, we call Jupiter a gas giant because it's composed primarily of hydrogen and helium that was gas in the protoplanetary disk that was accreted onto the planet. There are heavier elements in Jupiter, but they sink to the core, where there's very, very high temperatures and pressures. And in fact, the pressure inside Jupiter is so high that the hydrogen in the interior of Jupiter is not gas anymore at all. It's actually what we call metallic hydrogen. And in this case, we mean metallic in the sense of like metal, not astronomy metal. And that it becomes a conductor of electricity, and it's actually more of a liquid in this phase than a gas. And at the very center of Jupiter's core, the temperature is estimated to be 20,000 Kelvin with a pressure of over 4,500 gigapascals. Remember, giga means a billion, so 4,500 billion. It's a lot. Now, it used to be thought that these heavier elements that were located in the core of Jupiter formed kind of a solid core on top of which you had these metallic hydrogen and then the gas atmosphere. However, recent measurements in the past 10 years or so have revealed that Jupiter's core is actually more diffuse than that. That it actually was a lot of mixing between the center core and what we might consider the mantle of Jupiter. And so scientists actually call this a fuzzy core because it's not the traditional solid ball with layers on top of it. It's more mixed than that. And then this atmosphere of hydrogen and helium that's on top, you'll often hear it called an envelope or an envelope, depending on how you pronounce words. So that's just another word for the atmosphere of a planet. Now, this atmosphere is actually what we're seeing when we look up at Jupiter in the sky, because that's the top layer of the planet. And in fact, the inner parts of Jupiter are completely shrouded by clouds. There's a top cloud layer on Jupiter that's about 50 kilometers thick. Now, for reference, the Earth's entire atmosphere is about 100 kilometers thick, so this is a pretty thick layer of clouds. And these clouds are mostly formed of ammonia. They also tend to vary with latitude on Jupiter, and that's what gives Jupiter its very distinctive banded look if you've seen pictures of Jupiter. And these lighter bands are called zones, and the darker bands are called belts. Now, I said that these clouds are primarily made of ammonia, so they're not at all like clouds here on Earth. But underneath the ammonia layer of clouds, there might in fact be a layer of water clouds, complete with thunder and lightning, which is pretty cool. There's also a phenomenon called shallow lightning that happens within the ammonia clouds, but that's a little different than what we would get here on Earth. Now, these different bands of clouds have different wind speeds and wind directions and different circulation patterns, and so this all leads to very, very high wind speeds on Jupiter and a lot of turbulence within the atmosphere. And so this leads to things like storms. Very famously, one storm is called the Great Red Spot. Now, this spot has existed that we know of for at least 200 years, possibly 400. And although it has actually shrunk over time, it is still in the present day larger than the entire Earth. So this is a perpetual storm of huge size in the upper atmosphere of Jupiter. Now, I said Jupiter is in the outer solar system, so it's actually located out past the asteroid belt. It's about 5 times further from the sun than Earth is, which means it has a pretty long period. It takes almost 12 Earth years for Jupiter to go around the sun. However, the sidereal date on Jupiter is only 10 hours. Yes, Earth hours. So that monster of a planet is spinning over twice as fast as Earth. So it is going around really, really rapidly, and this is part of why it gets such epic wind speeds. We think that Jupiter was the very first planet that formed in the solar system because it had to form early enough in the life of the sun that there was still plenty of hydrogen and helium hanging around the protoplanetary disk that could be accreted onto Jupiter to lead to its really enormous mass. But exactly where Jupiter formed is really not known. So we do think that it formed somewhere in the outer regions of the solar system because there's more solid material in those regions because there's ice in addition to things like dust. And this extra solid ice helps Jupiter to kind of suck up all that material it needs to become a giant planet. However, planets tend to interact with the disk that they are born in, and they tend to move around and migrate. They can interact with other planets. In particular, Jupiter interacted probably a lot with Saturn. And so we really don't know for sure what happened leading up to the present day configuration of the planets and Jupiter. One kind of leading model is called the Nice model, named after the city in France. And the Nice model proposes that Jupiter and Saturn were in a special orbital configuration called a mean motion resonance. In this case, a 2-to-1 mean motion resonance. So basically Jupiter orbited the Sun twice for every one orbit of Saturn. The end result of this model is that Jupiter would have moved slightly inwards from its birth location to where we see it today. A somewhat more dramatic model is called the Grand Tack model, and this model hypothesizes that Jupiter actually migrated very far inward in the disk, all the way up to about 1.5 AU, so just a little bit farther than Earth's current location. And then at that point, it turned around and migrated back outwards, again thanks to a 2-to-1 mean motion resonance with Saturn, which would have also been migrating inwards with it. There is also a modification to the Nice model called the jumping Jupiter scenario, where basically Jupiter's position changed very rapidly instead of this kind of more slow migration process. Basically, it's really still an open question of exactly how the solar system's history played out, but regardless, Jupiter definitely played a really important role because it is so massive, so it kind of just throws its weight around a lot and has a big effect on other planets. But let's go from theory to observations. So Jupiter is actually the fourth brightest object in the night sky, the second brightest planet after Venus, although sometimes Mars sneaks in there as a little brighter depending on the configurations of the planets. And as such, it's been widely observed throughout all of human history. The earliest records we have are cuneiform records from the ancient Babylonians back in the 8th century BC, recording the movements of Jupiter through the sky. Jupiter's orbit around the sun, which takes almost 12 years, is basically the part of the basis of the Chinese zodiac, which is a 12-year cycle. So of course, in the 17th century, when the telescope arrived, one of the first targets was Jupiter. So Galileo observed Jupiter in 1610, and he noticed the 4 biggest moons of Jupiter, which nowadays we call the Galilean moons, although the actual individual names of the moons were taken from a different astronomer. And in fact, the movement of these moons around Jupiter, which was very clear, was a really major piece of evidence in favor of the Copernican model, showing that basically the Earth was not the center of all celestial motion because these moons were clearly going around Jupiter and not around the Earth. Galileo was a big advocate for the Copernican model. Now, although these 4 are the largest moons, we actually nowadays know of 79 moons of Jupiter, and that's not counting the really tiny little bodies that get caught up by it. So there's a lot of moons around Jupiter. So then with a slightly better telescope in the late 17th century, Giovanni Cassini observed Jupiter and discovered some more details, including seeing the spots and bands for the first time, noting that it is slightly oblate, that is, it's wider at the equator than at the poles, noting that there was differential rotation, that is, not all parts of the atmosphere rotate at the same speed. And possibly he noticed the Great Red Spot, although that's not confirmed. And then also around this time, the timing of the transits and eclipses of Jupiter's moons were noticed to vary depending on how far away Jupiter was from the Earth. And this, in fact, was taken to be evidence of the finite speed of light. And the Danish astronomer Ole Romer actually used this to make the very first measurement of the speed of light, finding that it took light 22 minutes to cross the diameter of Earth's orbit. Now, he was in fact slightly wrong about that because the actual time should be 16.7 minutes, but it's pretty dang close for the very first ever measurement of the speed of light, which previously wasn't even known if there was a speed or if it was infinite or not. So it's pretty cool to look at Jupiter from Earth, but what about visiting Jupiter? Now, Jupiter doesn't have a surface as such, so there's not any way to put a lander on Jupiter, so all of the Jupiter missions have been either flybys or orbiting missions. The very first flyby of Jupiter was done by the NASA mission Pioneer 10, which launched in 1972 and flew by Jupiter in 1973. We actually had contact with Pioneer 10 for another 30 years after that, until it was finally lost in 2003, at which point it was a distance of 80 AU from the Sun, which is pretty crazy. And in total, there have been 7 probes that have done flybys of Jupiter. Now, the first Jupiter orbiter was the mission Galileo. This was launched in 1989 and placed into Jovian orbit in 1995. It also carried an entry probe that was released into Jupiter's atmosphere and took data until it was destroyed in less than an hour. And Galileo took lots of awesome data until it was completed in 2003. And upon completion, the probe was deorbited and burned up in the Jupiter atmosphere to prevent any possibility of contamination of the moons. Then the follow-on to the Galileo mission is the Juno orbiter, which is actually still currently operational. Also, can we take a second to appreciate the name, because Jupiter and Juno? Juno was Jupiter's wife, and Jupiter was kind of known for being a bit of a ladies' man, so sending the Juno probe out to keep an eye on Jupiter, I appreciate that. Anyway, Juno was launched in 2011 and placed into its Jovian orbit in 2016. Now, the original mission was planned to go only to 2018, but it's actually been extended as of now until at least September of 2025. The data that we received from Juno orbiting Jupiter is actually what led us to this conclusion about the fuzzy core that Jupiter has, and it takes like the most amazing pictures. This is actually my current computer background, because how can you beat these amazing views from Juno? Because Jupiter is indeed beautiful and amazing and truly well-named king of the planets. So thanks for journeying with me to Jupiter today. I hope you will join us next time as we journey on to Saturn. Thanks so much for watching. I hope you have a good one. Bye!